recording. So far what we've done is electrostatics. We're looking at just static situations where charge is just sitting there. It's not moving around. Not really. We talked about somewhere what would happen if we moved it from point A to point B. We didn't actually talk about what was happening really during that motion so much. Just we had a set of static charges and they were doing something, right? And that was it. You know, what would they do if they basically all didn't move? Very little movement was going on. Well, now we're going to start talking about what happens when they move. Then the first things we're going to do here when we start talking about how they move is we're going to talk about electric current and circuitry. That's when we actually start getting charges to move through wires and things like that and through components, and we start getting some electrical systems going, all right? That will lead us into the next chapter, which will be moving charges, which will be magnetism, all right? So let's go ahead and get started here. First, we're going to start talking about electric current. Then we'll talk about resistance to that electric current. And it basically sounds exactly like what it sounds like. It resists electrical current flowing through it. And then Ohm's law that helps us calculate this resistance. Energy and power in these electrical circuits. Different kind of components we can put in there, which will be resistors. And we'll also look at capacitors in these circuits. And then we'll look at resistors and capacitors in there at the same time. And then ammeters and voltmeters, these are ways to measure voltage and the amount of current flowing through something. And so let's get started with the definition of electric current. So electric current is the flow of electric charge from one place to another. What our definition here is, we represent electric current with the capital letter I, and it is a change in charge, so it's the amount of charge that flows per unit time. So you go to one little spot, you look at it, you want to know the current through it, you sit there and you watch the number of electrons or the amount of charge that goes by in a certain amount of time, and you divide them and you're done. Kind of like if you wanted to know the amount of water flowing through a river, then you go there and count the amount of water that flows past it in a certain amount of time. And you'd have like a flow rate. So this is a rate, right? Anytime you have that, you see that rate means divide by time. So this is the rate at which charge is flowing through something, okay? And our SI unit for this is the ampere, or often called just the amp. And it's the capital letter A, and it is a coulomb per second. Charge is in coulombs, and of course, time is in seconds. All right, now if you go to an electrical engineering class, they will use a lowercase I for current quite often. And then you say, wait a second, what do they use for the imaginary number then? And it turns out they'll use a lowercase j for the imaginary number. I don't understand it. I don't try to understand it. They're, part to themselves, I guess. And there is a lot of imaginary numbers, not in what we're going to do, but imaginary numbers show up a lot in electrical engineering and circuitry. They show up a lot. So they have to deal with that a lot. I don't know how they ended up with that lowercase I and then switching imaginary numbers to J, but that's what I've seen of them in the past. What's that? I don't know what they use the capital I for. They're just not using it as far as I know. So, all right, so that's our charge per unit time. If we make a closed path through which we can get this current to flow, that's our electrical circuit. Okay, so basically, the first one we'll look at here is a regular old battery. Here, we're using chemical reactions to create a voltage. Just to simplify it way down, you've probably done batteries in chemistry. But the idea is you have a chemical that wants to give up electrons and you have a chemical that wants to gain them, and you give them away to exchange, right? That's the basic gist of it. And you do that by usually connecting them through a wire, which can carry an electric field through it very well. And so the electricity will then flow through that wire. So you're using that chemical potential kind of a thing. And you get it to flow through. A light bulb is essentially a resistor. If we're talking about old incandescent light bulbs, all that means is you try to push electricity through them and they resist it. They resist it so much that it gets hot and it glows. Kind of like if you've ever seen a hunk of, steel or iron or something that put in the fire and you put and it's glowing, right? It's called black body radiation, but you pump the current through the little filament. It has a high resistance to it. It creates a lot of heat. It gets so hot, it glows. Those are the old incandescent light bulbs. The light bulbs that are in here, which I think are fluorescent light bulbs, they are a little different. You're passing an electrical voltage through a very low pressure gas such that it creates a type of plasma that then emits ultraviolet light. The reason it's called a fluorescent light is because you then coat the inside of the glass with a fluorescent material that absorbs that ultraviolet light and instead emits two lower energy lights that are in the visible range and you can see it. If you take that coating off, then they're just UV lights and it's very bad for you. In fact, all right, so basically the idea here is if we look at the circuit, we have a little switch here. If you close the switch, what allows to happen is we have a voltage across here. So we have a low voltage here and a high voltage here. And we connect them with the wire. This then pushes the electrical current over here, goes up, goes through the wire, through the little filament, comes back around over here where it ends on the other side of the battery. All right, while it goes through this, creates heat, lights it up. Now we're getting lots of lights like LED lights. They work through a different process that has to do, well, it's a junction between an N and P type semiconductor. I don't know what y'all know about semiconductors, but it's a different process. It doesn't create the light through heat. It creates it through transitioning from two different types of dope, two differently doped semiconductors. Anyway, we don't need to know that. And then they're equating this here to someone standing there and dumping water at the top of a paddle wheel and then letting it flow back down in terms of the paddle wheel, which is where the light would be. And then they keep doing that. And that's what the battery's doing. It keeps adding energy into it, which keeps pushing the electricity through. Okay. Next here in the electric circuit, a battery. So a battery is disconnected from a circuit. It has an electrical potential difference between its terminals. That is called the electromotive force, or EMF. This is an extremely unfortunate name because it is not a force. It is a voltage. All right. We have two different kinds of voltages we have to worry about here. We have to worry about supplied voltage. This is via it being plugged in or attached to a battery. These are sources of potential, like a battery or plugging into a wall. Those we call EMFs, electromotive force, and we use the Greek letter epsilon there to represent it, but it is still a voltage. And then we have voltage drops, where that potential gets used up as it pushes electricity through different parts of the circuit. All right, so be very careful as we go through this to make sure that you're keeping those separate. One is a source of voltage and one is something using it up. Like if you're the person putting the ball at the top of a ramp and then the ramp uses up the potential energy as it goes down it. You're providing the potential energy, the ramp is then using it up, kind of a thing, all right? So be very careful about that. The amount of work it takes to move a charge, delta Q, from one terminal to the other, just going for magnitude here. Remember, voltage is work per charge or potential energy per charge, which will be our work per charge. And so we can see here that you just multiply both sides by Q and you get that work is just the charge that's moved times the applied voltage. So the voltage of the battery. Okay, the EMF. So be very careful with this. It is an electric potential. All right, it's a voltage. All right, we okay with that? EMF. Next, electric current. So before we look at that page, there was a big problem. Physicists came along, or whoever they were, I don't want to take credit for them, and they said, all right, we need to figure out, we know we have electricity flowing, but is it flowing from positive to negative or negative to positive? Which way is it flowing? Because no matter what experiment they did, looking at it either way was equivalent. It gave the same results, the same answers, and we saw the same things physically. So you got to go and use some logic on this, right? Things in nature tend to flow from high to low, right? If I put something at the top of a hill, it will flow from the high point to the low point. You don't typically see a ball rolling from the bottom of the hill to the top, right? That doesn't really happen. Things go from high to low. You hold something up high, it drops to down low. Okay, so that's what things in nature do. So logically speaking, current would also do the same sort of thing. It would go from high, positive, to low, negative, correct? Flawless logic, everybody agrees with this, correct? Except it's not right. Except it turns out that is a mistake. Okay? Why is that a mistake? All right, let me ask you one other different question. Why are they named positive and negative? Just because they chose it. Could it have very easily been chosen the other way? Could they have chosen like up and down? It was really just to show they were opposites, right? So does it make sense to base a scientific principle like we think this is actually what's happening based on just basically arbitrarily chosen names? No, it doesn't. It doesn't make a lot of sense. Turns out it didn't work out and it was wrong. However, we were so far into it, so much had been done, so many books had been written, so many things had been done with it, that by the time it was figured out that it was the other way around, we were dug in. So we basically have to worry about two things here. Makes it slightly more confusing for y'all, but it all works the same here. You have to worry about current, sometimes called conventional current, which we treat as the flow of positive charges from the positive side to the negative side. And then we have actual electron flow, because we found out that the charge carriers are actually the electrons, they are the negative ones, and they flow from negative to positive. Okay, so those are our two different things. So the current we talk about, current is, you treat it as though it's positive flowing to negative. It just turns out technically, physically, it's not. When we get into magnetism, if you want to remind me, I will explain to you the experiment done that shows that it's the negative charges moving and not the positive ones for this type of current. Okay? But otherwise, it gives you the same answers either way you do it. So we'll just stick with the positive current rather than going back and rewriting all the books and doing all those changes. It's kind of like pi versus tau, right? Tau is far superior, but nobody wants to go back and rewrite all the books and change it all and do that kind of stuff. So we leave it. And those of you who had me for math probably remember me talking about that. So, and if you don't know what tau is, you ought to look up the Tau Manifesto and watch it. It'll totally change your mind on whether or not you should be using tau or pi, because pi is 3.14 and tau is 6.28. Okay, so take a look at that sometime if you ever have some time. So that's what our current is going to go. It's going to go from positive to negative, but the actual electron flow is from negative to positive. It doesn't matter for most circuits. So it works out equivalently, so we leave it. Now, the actual motion inside of the electrons inside the wire is not just straight through. It bounces around zigzag as the electrons bounce around, being deflected by the nuclei and probably other electrons as well. And they don't go just straight through. So even though the electrons themselves have a very high speed, their overall propagation through the wire is actually slow, down on the order of centimeters per second. A great example of this that I'm sure you have all seen is you were probably in your house or something sometime, and you're over here and you're on the wall and you flip the switch on. And then the light in the middle of the room, you have to wait as the electrons flow up slowly, centimeters per second, go up here, go all the way across the room, and then finally turn the light on over there. We've all experienced that, haven't we? Every time you flip the light on, it takes what, a good 10 or 20 seconds before they turn on, correct? Oh, sure, any of them. Any lights, you flip them on, you have to wait all that time for the electricity to flow all the way up there. No, that doesn't happen, does it? You'd be surprised how many people agree with me that that happens. No, it doesn't happen. So am I lying to you about the speed of the electricity or what? Because obviously we flip the light switch on and it's like immediate the lights start turning on. But I'm sitting here telling you they only move at a few centimeters per second. There you go. Because you don't have to wait for the electron that's right here to make it all the way to the light lighted up. There's already electrons already in the wire. And as soon as this one pushes, the actual propagation of that signal, as soon as that first one moves, the electric field moves all the way through it, that little change in the electric field, and basically at about the speed of light, almost the speed of light, not quite, the ones at the other end will start to move. All right? This is why you can, you talk to someone. Otherwise, if you tried to talk to someone on the phone and you were using like the old wire for the phone, for fiber optics and stuff, you don't want to talk to someone like over in California, stuff, you'd say something and then you'd set the phone down and come back like a week later to hear their response, right? Because it would wait for centimeters per second for it to get way over there, right? And then for them to reply and for hello, and then come back. But that doesn't happen. So the actual signal that the electricity has started to flow happens very quickly. It propagates very fast through the wire near the speed of light. And it happens very, very, very quickly. Now, I did look up and find one of these to demonstrate. Let's see if we can get this. To demonstrate how the electron, and it always makes me think of Plinko. Y'all ever see Plinko on The Price is Right? Here, let's keep going. Here's Plinko. So, guess all this stuff, they win, and then they have to go do this. So they get at the top, there's all these posts and stuff, they have these little discs they have to drop. And it'll drop down through there. And so they pick a place, and down at the bottom you have different numbers, but watch the path as it goes through, as it bounces around. It doesn't just fall straight through. So even though the Plinko disc is moving kind of quick, its overall progress down flowed by it bouncing up and down and around and stuff like that. Okay? See, it bounces around, moves, goes back up some, comes down, moves up. I wouldn't mind getting that. Okay? Now he's a little excited. So basically it bounces around, in my mind, like Plinko. It's bouncing around between the cores of the atoms and stuff like that, and bounces and bounces and bounces and makes an overall progress through. And that overall progress through is actually called the drift velocity. Here, what we have is something called Ohm's law. Under normal circumstances, wires present some resistance to the motion of electrons. It's usually pretty negligible compared to the other stuff we're looking at. Unless you have to be really, really accurate with your circuitry, you usually can ignore it. But we have something called Ohm's law, and it tells us that the voltage across a part of a circuit is equal to the current flowing through that circuit times the resistance of that circuit. So the voltage drop across it, in other words, how much of that voltage will it use up, is equal to I times R. The SI unit, of course, for this voltage being voltage. It's the same voltage we were talking about before. It is our potential to move a charge. So that's what it is there, and that's how it relates to our current and the resistance of the material that we're trying to push that through. Now, Ohm's law does not work for every material. It does not always work. It works, and when it works, you use it. And when it doesn't work, you don't use it. So there are certain materials that are called ohmic materials, and they are called that because they obey Ohm's law. If they do not obey it, they are non-ohmic materials, and you don't use Ohm's law. It's as simple as that. The resistors that we're going to be talking about shortly, they will be ohmic resistors. They will work with it. Okay? Yes?
So like, why is it like, what factors are different between
There are some things like a capacitor. where as the voltage drop across the capacitor goes up, the current actually goes down. So we'll get to that shortly. There are some things where frequency will matter. Like if it's an alternating currents, the different frequencies will change how this works. And so therefore doesn't quite fit with this kind of a thing. So really it's just kind of material based and the situation based. But usually what we're talking about here is resistors where most of it will work. Okay. Inductors, capacitors, things like that we haven't talked about yet, we'll get to. Okay, so that's Ohm's law. Just be careful. Most conductors it works for. If you solve for resistance, you can get R equals V over I. You just solve it. The units of resistance are volts per amp, and we call that an ohm. Fits nicely with our Ohm's law, right? In an ohmic material. It's an ohm. And we use that Greek letter omega. Okay? And what letter of the Greek alphabet is omega? Huh? It's the last one. Yeah. The alpha and the omega. Right? Beginning and end. So 1 ohm. So you'd have different ohm resistors. The greater that resistor, the greater the resistance, the harder it is to push electricity through it. Okay? It's a very descriptive name. It resists electricity flowing through it, current flowing through it. All right? Here, what we have is something called resistivity. We use the Greek letter rho for this one. I don't really like presenting it as resistance equals rho times L over A because I feel like that makes the resistivity depend on the resistance. I mean, I guess that kind of works, but no. You know what? I'm okay with that. But you can also think of it this way. And I see this in a lot of other books. Maybe I'm not a bigger fan of that. But sometimes you see it written as RA over L, where you swap the resistivity and resistance. Okay? So if you think about it here, we'll use it this way. If we think about it this way, you've got what is it that determines how much total resistance a certain wire or object has to stuff going through it. I like to think of a road here. All right? So there's a few things that can affect how quickly traffic and how much traffic can flow down a road, right? First thing is, how long is it, right? How long is it? The longer it is, like say it's like a dirt road, like think of it this way, not a nice clean road. Let's say there's a part of the road where they're redoing construction on it. Well, the longer that construction is, right, the more it's going to stop the flow of traffic. So that's where that L in the top comes from, that length. The length of the resistive part of the road, where they've torn up the road or something like that, and people are having to slow down because it's all gravelly, or there's a lot of potholes in it, it's a poorly conditioned road, and so you can't just fly over it. Not a nice smooth road with no resistance. And so when you're in that part that has resistance, the longer that resistance is, the harder it is to get through it, right? The second thing that matters is how many lanes. How wide is it? Is it a single lane? Is it all dropped down to 1 lane? Is it 6 lanes? Is it what? The more lanes there are, the more cars can go through it at the same time. That's the area on the bottom. All right, that's the area on the bottom, the cross-sectional area of the wire. The thicker the wire, the more electrons, the more current can flow through it at any single given time. It can spread more, and more can get through. So it's that cross-sectional area. And then, of course, lastly, is that resistivity. That is the condition of the road. A couple of minor little bumps or speed bumps is probably not going to slow you down as much as giant potholes all over the place, or the road being flooded and you having to slow way down for it. So these are the things that determine what the overall resistance is in your wire. The resistivity is like a material property. The length of it is, again, it's how long do you have to stay inside that bad part, and then the cross-sectional area is, how much of that current can you start flowing through there simultaneously. All right. L tells you basically like how far through it you through. So you can imagine if I said, all right, I'm going to take a really resistive material that's, a centimeter long, and I'm going to try and push electricity through it versus one that's like 5 meters long. It's going to be a lot harder to push it through that 5 meters. And it's going to be, so there's going to be a lot more resistance to there. Okay. Any questions?
So just real quick, so if it increases in length, it increases in resistance.
Yep.
If it increases in area, it decreases in resistance. If it increases in resistivity, then it increases.
Yes. So essentially what you have is a length to it, to your wire, right? You have L, the length. You have the material property rho, the resistivity, and then on the end, you've got a cross-sectional area of your wire, right? Area, length. Okay. And of course, if you make it a larger wire, aren't you going to be able to get more to go through it? Kind of like if you have a larger pipe, right? More water can flow through it than, like those little coffee stirrers. It's a lot harder to drink through those than through a normal straw, right? Those little teeny skinny ones, right? Yeah. Yeah. Okay. Any other questions on that? Yep. It's a rho, Greek letter rho, lowercase. Yep.
So you compared resistivity to like the condition of the road.
Yeah.
So maybe this is intuitive, but like if your wire gets damaged, then that's always gonna slow down the flow of.
What do you mean by damaged?
Like, well, I don't know.
Like if we cut a chunk out of it and reduce that cross-sectional area, then yes.
Okay.
But that's not the material property anymore. That's through the cross-sectional area. The way you would change the resistivity would be something more like introducing impurities to it, like an alloy.
So
All right.
It has to be more material.
Yes, that is a material property.
That helps a lot. Thank you.
Yep. Yep.
So if the wire was like frayed, would the area be less? So it would be,
If it's frayed and it's not all connected anymore, then yes.
just in that one spot for the whole thing.
Well, it'd be like a bottleneck, right? So, like, I don't know how to describe it better than a bottleneck, right? It's
So would it like move at the same speed and then slow down and then speed back up?
no, I mean, it can't go faster, right? It's like even if you see all the cars are creeping through the one, it still slows them up there. It still, piles up behind them. Maybe if you're far enough away, it's, it lessens and lessens just like in traffic, but no, it would slow down everything. Okay. Doing okay with this so far? Yes.
Just one more. Like,
No, go for it.
It's backtracking a little bit, but I feel like this is totally going to confuse me a lot later because we said that charge and electrons flow in different directions, in opposite directions.
I said current
Current.
and electrical, and the electrons are opposite.
Isn't current like charge over time?
It's supposed to be, but it was a mistake.
So-
Remember? But it still works, so we still use it. It's mathematically equivalent in almost all cases, except in one that I'll show you after we get to magnetism.
So current and electrons don't flow in opposite directions.
Current flows from positive to negative. The actual charge carriers, the electrons, flow from negative to positive. But they are mathematically equivalent.
Right. Just the sign would be different?
No,
No.
they are mathematically equivalent.
Okay.
Would it kind of like be just ignorant to absolute value of it?
No, it would be like going through to all your equations, changing I to negative, but then also changing the direction to negative, and therefore they cancel out, and you have the exact same thing again.
So could you just decide if the other one positive and negative?
Yes, you could have. So by the flip of a coin, we got like unlucky there, I guess, in that it went the wrong way, and now y'all have to ask this question. Sorry. If I could go rewrite all the books and change it and just stop teaching suddenly, I'd probably go ahead and take that. But I mean, you look at that causes issues if y'all try to work with people who are already through school later on. Like if you go become an electrical engineer and you have to talk to one of them and then y'all are saying the opposite things, kind of like that probe they sent to Mars that crashed and they couldn't figure out why at first. It just disappeared. And then they realized that one group was working in like miles and the other group was working in kilometers, and they didn't know that. And so their numbers didn't match up because they were working in different systems. So convention, it's easiest to go with convention sometimes so that we're not all, we're all speaking the same language, I guess, you know? Yeah.
Would there be a difference in that concept of like conceptual questions and mathematical questions, or is it the same thing?
There are some conceptual places where it can differ, which I'll show you when we talk about magnetism. We need magnetism in order to set up a situation where we'd get a different result, treating it as positive flowing or negative flowing. Because otherwise they all turn out the same. If everything we're going to do, they turn out the same. But yes, conceptually, you should know the electrons are the ones that are the charge carriers. They are typically the ones moving here, and they're moving from negative to positive. But we treat current conventional convert as the positive charges flowing from positive to negative, and it goes that way. But if you switch it, again, it just double negates, and you're back to the same results you had before. All right, anybody else? Okay, here are some resistivities of different materials, different insulators, semiconductors, and conductors there. So you can look at, you notice the resistance is very high for the insulators, especially compared to the conductors. And then the semiconductors, it depends on how you dope them. Right? They can be conductors or not conductors, depending upon the impurities or lack thereof in them.
So resistivity is resistance for the units, omega times times
The resistivity,
yeah, what about
it would be, what is that, an ohm? Yeah, like an ohm meter. Area over length would give us just a meter left, and then the resistance is an R. Okay, which I guess we have right there, ohm meter. Okay, yeah. How about this one? Copper. You were asking the question about the damaging it. Copper oxidizes. And when copper oxidizes, it doesn't conduct electricity as well, right? So that changes the resistivity of it. So one of the things that they do is they coat the ends of wires in gold, because gold is very inert and doesn't oxidize, right? So you coat the ends in gold. This is what they typically do on the higher end, like connections for TV screens and stuff like that and sound equipment. Gold is actually a worse conductor than copper. You can see that here. It has a higher resistivity, and therefore would be a higher resistance for the same situation. Right? See them right there? But by doing this, you coat the outer part, the part that's exposed to air, in gold, and it won't oxidize. And it prevents the copper on the inside from oxidizing, and therefore you keep that nice pure copper for your very good signal conduction through it, or your electronics and stuff like that. There's an example of, I guess, that for you. Oxidizing it would change it, but then it's a material property, not like a physical damage. The physical damage would change like L or A. Okay, and then of course silver, real low there, but silver is a lot more expensive than copper. All right. In general, not always, the resistance of materials goes up as the temperature goes up. This is not true for semiconductors. But basically, typically, the higher the temperature goes, the greater a resistance you get, because you have thermal effects. Could you imagine that Plinko board now trying to drop something through it? But now all the little posts are shaking around. It's going to be a lot harder for that Plinko thing to make it through that right then, isn't it? If they're all shaking around more compared to them just sitting still. So as far as metals go, conductors, the lower the temperature, the lower the resistance or the resistivity. You can use these kind of ideas to help make thermometers. I think y'all were using some of them this week. A little wire that you put down in there, and then it can change that, which changes the voltage, and it can read that and tell you what the temperature is. Resistivity decreases as temperature decreases, but there's a certain class of material called superconductors in which the resistivity drops suddenly to 0 at a finite temperature, called the critical temperature. All right, aluminum will do this. All right, and this is one of these things we thought we had understood until people started actually finding type 2 semiconductors that, you know, this was normally would only work at very cold, near 0 Kelvin, but only like 2 or 3 or 1 or 4 Kelvin. But now they found I think it was even accidentally found the type 2 semiconductors, which would be superconductive at like 100 and something Kelvin. The great like gold mine would be finding room temperature superconductors. Okay, this is materials that are going to flow electricity with no resistance to it. All right, so you can imagine your cell phone batteries lasting way longer because they don't have to create heat as electricity flows through it, especially if it's like a cheap material. We suddenly would have, you know, a lot less power demands and power going down the wires to your house. There's a lot less loss due to heat and stuff like there is now, and things would become way more efficient. If it's really a cheap enough thing, you can start, you know, working on flying cars and stuff like that can use use magnetic levitation and stuff like that. It would be a very big jump forward, right? A big revolution in technology. In fact, this is what a pretty famous movie is about. It has some blue aliens in it. They go to the planet and they're after that rock. Avatar. That's what that rock was. In fact, they called it unobtainium. That's actually an old physics term where people would say, we're going to make a frictionless surface. And someone would say, how do you make a frictionless surface? Well, you make it out of unobtainium. So I remember I went and saw that with some friends, and they were mad. They said, that was such a dumb name. And I thought, no, that's an actual physics thing like I have heard. You know, how do you make a massless pulley? You make it out of unobtainium. And so that's what they were saying about this stuff, is it was this great material that had all the properties they want, which was being a room temperature superconductor, which is why those mountains floated, which is why he stuck it on his desk and it floated there. That's why they wanted it so bad. It was an extremely valuable room temperature superconductor. That's what they were there for. And they expel all magnetic fields. So superconductors, they will float if you put them in a magnetic field. So they were at the poles where they talked about the flux vortex being super strong because they had very strong magnetic fields there, and the mountains would float up because it was full of that rock. So it wasn't supposed to be magical. It was supposed to be scientific. Just in case y'all were wondering about that. You know, maybe makes that movie a little better. The magic's gone, I guess. Okay. Energy and power in electrical circuits. So, of course, potential energy, a change in it is Q times V. And then power is work per unit time, right? Y'all remember power? In the units were watts. Right? It was a work per time, the rate at which you could do work. And so that's our change in potential energy per time, which is QV over time. Q over T is current. And so P equals VI. Power equals voltage times current. Okay? This is how you make voltage regulated things. This is why you can have I talked about it before, like the stun guns that have 100,000 volts but they're not deadly because they don't have much current. Because what you do is you take this, it has the same power, you put like a 9-volt battery in it or something, and what you do is you use these little transformers that jump the voltage up to 100,000 volts. Well, in order to conserve energy, power has to be conserved because power is energy per time. And so as voltage goes really high, if we're keeping power the same, what has to happen to the current? It goes really low. And so those things give you a big jolt with a high voltage, but they don't push a lot of current in through you. So it's not going to stop your heart. At least that's the idea, right? I guess if you have something wrong with your heart or you have a pacemaker, it could mess with that. But for the most part, they're supposed to be non-lethal. And it's because of that. P equals VI. So, and they do that the same thing to send electricity to your house. They jump the voltage up really high on the power line. So very little current is actually pushed down the line. They just push the potential. And then when it gets near your house, it goes through a transformer that drops the voltage down to the 120 volts that you can use and then actually gives you current that you can then use. So they send you voltage and just, it gets to your neighborhood and turns back into lower voltage with higher current. You can combine, I don't recommend memorizing these other two here, but you can combine this with Ohm's law. P equals VI, V equals IR, so replace V with IR and you get P equals I squared R. This is if you have a situation where you are given current and resistance and you need to find power. And you don't have the voltage. You can just do that. Same thing down here. P equals VI. I is V over R from V equals IR from Ohm's law. And so P equals V squared over R. Point is, you typically use V equals IR with P equals VI. You're going to use those two together a lot. Okay, so don't be afraid to combine them. Any questions on that? All right, I think I'll stop there. We'll do that next. I don't think 2 minutes is enough, but hold on a second, and I'm going to stop.